So you may have heard me say in one of my earlier lectures that one of the main things that we're trying to do with this course is we're trying to answer the question of will it break, right? Like that's kind of our big theme for this class, is being able to predict how much force or stress a part or assembly might be able to take before you get in trouble because it might be close to breaking, okay? And one of the things that we're going to study, it'll be a few class periods from now, but one of the things we're going to study is one of the ways that we can quantify how close a material is to failing is with something that's called strain energy, okay? So it kind of turns out that there's only so much energy per unit of volume that a material can carry, and after a while it says I'm carrying too much energy, and it might break. That's an oversimplification of how it really works, but we're going to get to how it really works pretty soon. But I want to give you an idea of why we're talking about strain energy today. And the reason we're talking about strain energy is that it will end up connecting very closely to answering the question of whether or not we're close to breaking a piece of material, okay? The other thing that we need to discuss a little bit here toward that end is this idea of transverse strain, okay? We're all kind of familiar, I hope, with the idea of strain, and that is when you put a stress on a piece of material. So let's say this is a piece of material that I start to pull on, right? I put stress on it when I start to pull on it, and it might deflect a little bit. It might actually elongate a little bit once I start to pull on it. If it elongates a little bit, then we can define the strain in terms of how much it has elongated divided by what its original length was, right? That was the definition of strain that we've talked about before, okay? And so I have that up here. That's this little formula, and that's kind of the part of it that everyone should be totally familiar with. The part of it that we talk about usually a little bit less is that not only does your part that you're stressing along this axis, not only does it elongate a little bit in that direction, it actually gets smaller in the directions that are perpendicular to that. And that's called transverse strain, okay? You actually can see this if you have a rubber band, which I actually happen to have in my pocket here. If you have a rubber band, you can actually see this happen with a rubber band. As you stretch it, what happens to the rubber band? Okay? It starts out being maybe a 1/4 inch wide here, and by the time I've stretched it out a pretty good bit, it's probably down to, maybe 3/16 or something like that. It has actually sucked down and become smaller in the direction opposite the direction that I'm actually pulling on it, okay? And this tendency of material to do that matters when we start talking about strain energy. And so that's why I bring that up right now, is that not only does a material strain in the direction you are stressing it, it also strains transverse to the direction that you are stretching it. And that is a negative strain, right? It's going to strain, it'll get smaller if you have a positive stress, right? So, and that's, the parameter that we use to talk about this when we're dealing with real materials is this parameter called Poisson's Ratio. Okay, in this textbook, it's a Greek letter nu that we use to talk about Poisson's ratio. Okay, and that's, it is basically just a ratio that tells you how much it will strain transverse relative to how much it strains along its length. Okay, this value for most materials is somewhere around 0.3. Okay, so that it varies a little bit from material to material, but the amount that it varies isn't super large, all right? It's usually somewhere around 0.3. Might be a little higher, might be a little lower, but somewhere around there. That is an elastic property that is also given to you in Table A5 in the back of the book for various material families. All right, so let's actually, uniaxial stress is easy for us to think about. Let's think about biaxial stress, okay? That means we have stress happening 2 different directions, okay? And what you see there is for each of our directions, we can figure out how much a piece of material will strain based on stresses that happen in the direction that you're evaluating the strain, as well as a stress that would happen in a direction opposite the direction that you're evaluating the strain. Okay? So we basically, if you have a state of biaxial stress like this, you have to account for both the direct strain that happens due to the stress that you apply, as well as a transverse strain that occurs as a result of the stress in the other direction that you apply. Okay? So that's where these terms where we have like epsilon sub y, meaning the strain in the y direction, is equal to 1 over the elastic modulus times the stress in the y direction minus Poisson's ratio times the stress in the x direction, right? If you look at these, they kind of make sense. At least I hope so. Okay? They're using essentially Hooke's law along with the definition of Poisson's ratio in order to give you what these strains would be in each direction. Well, is that something that we could expand out to 3 dimensions? Okay, so we did a biaxial state of stress. What if we talk about a triaxial state of stress? Okay, and it winds up working basically the same way. What's the big difference that you see? Right, you have to multiply Poisson's ratio by the sum of the 2 stresses that go the opposite direction of the direction you're trying to evaluate strain. Okay, and again, that kind of makes sense. You know, both of those would contribute to the strain that happens in that direction. You know, so it makes sense that we would have to plug both of those in and multiply it by Poisson's ratio. Okay, all this good so far? Okay. So let's leave that alone for a second, and we're going to go into another piece that we need to evaluate this idea of strain energy. Okay? And it requires that we kind of think about the idea of energy that's applied into a piece of material when you begin to load it with a force. Okay? So the figure that I'm showing you here has a force of F that's applied to the end of a uniaxial rod, right? It's just one axis that we're applying stress to, and as we apply the stress to it, let's say that stress causes the rod to strain, and by straining it creates a little elongation that I've called delta x right there. Okay? With me so far? All right. We can figure out what the stress is that's being applied by taking F over A, right? And we can figure out what the strain is by taking delta x over L. Do you agree with that? So I can relate my force and deflection to stress and strain just by the geometry of the rod that I'm elongating. Well, here's where kind of the root of the matter happens, is this idea of how much energy is applied. The amount of energy is basically based on thinking about, let's say there starts out with 0 force in it, and I apply a tiny little bit of force, okay? And it moves a tiny little bit. That could create like a little rectangle right here and say, I had to put some force times distance in order to get the thing to move, right? Because it has a force, F, and a distance, let's say a little delta x, right? And you had to put in F times delta x for that first little bit. Well, let's say you keep on pulling on it. You pull on it a little bit further. Okay? What happens then? Well, now you actually, this thing behaves like a spring, right? You keep on pulling on it harder, it's going to pull back with more force, right? And so you see there, the way that a spring works is that the amount of force increases as you begin to deform the material. Okay? So the next little bit that you have to deform it, you're going to have to put that much energy in. And then the next little bit that you have to deform it, you're going to have to put that much energy in. See what I'm doing there? Okay? And here's the thing. We don't want to think about putting in finite amounts of energy each time. In order to really make this accurate, what do you have to do? You have to evaluate this for such small steps that they are essentially 0, right? And what you see there is that what we're really doing is evaluating the area under the force displacement curve and that's the amount of energy that we had to put into the rod in order to get it to stretch. Okay, and this is just the definition of work. That's all I'm doing there. It's just definition of work, and we're sort of evaluating that we're putting energy in this way. Okay? Well, that energy that we're putting in, where is it going? Like, energy can't be created or destroyed, right? So where is that energy going? Yeah, it's stored in the material. It's stored because what we're doing is we are straining the material. If you could think about it, all materials are held together basically by particles, being bonded in some form or fashion, right? And you think about those bonds, and as you begin to deform this material, you're stretching those bonds. So that's where this strain energy is physically being stored, is in the bonds of the material. Okay? And so we can actually evaluate now how much strain energy we have put into this piece of material. And it's just going to be equal to 1/2 F delta X. Okay? Now I'm going to define another parameter here called strain energy density. And it might be approximately what you would think it would be. It's basically how much strain energy did I put into this piece per unit of volume. Okay, so you might imagine just how much strain energy you put into a piece probably doesn't really matter in terms of whether or not you're going to break it, whereas you might be able to have the intuition that a certain amount of energy per unit of volume, that would be a bigger deal, right? You kind of see that, like if you have more volume, you can have more strain energy, and it might not be any closer to breaking the material. All right, so we define strain energy density. Now let me show you this. The volume of this rod is equal to the area of the rod. I've got that shown right up here, right? Times the length of the rod, right? So that's the volume of the rod, is area times length, okay? Now I have the 1/2, that's where the 2 comes from. Now look at this, F over A, what is that? Stress. And what is delta X over L? Strain. Okay? And so what we end up seeing here is that 1/2 stress in a particular direction times the strain in that direction gives you your strain energy density. Okay? So 1/2 stress times strain in a particular direction gives you strain energy density. Now shall we make it a little more complicated? Okay. What we did last time is we looked at the uniaxial state, or the uniaxial state of stress first, and then we expanded that out to a multiaxial state of strain. So let's do that now for strain energy density. Okay. And here's a big distinction between the last diagram that I drew and this one. What we learned last time we met was that any stress tensor that you're given for an element of material can be transformed into 3 principal stresses, such that there are 0 strains, or excuse me, not 0 shearing stresses, right? So you can transform your whatever stress is given to you, whatever stress tensor is given to you, you can transform it into 3 principal stresses that are all normal. Okay? And I'm using a little notation here that's not necessarily standard across all texts or anything like that, but I'm calling sigma A, sigma B, and sigma C, I'm calling those my 3 principal stresses. And the reason I'm not calling them sigma 1, sigma 2, and sigma 3, you might be able to guess. Why do you think I'm not calling them that? So I don't want to specify which one's larger than any other, right? I'm just saying that sigma A, sigma B, and sigma 3, sigma A, sigma B, and sigma C, I'm just saying that those are my principal stresses. Okay? Now I'm going to submit to you as well that once you've found your directions of your principal stresses, those are also the directions of things that are called principal strains. Okay? So just like we have principal stresses, we have principal strains, meaning that once you find that orientation, if you were to have an element in that orientation, the element would not shear, it would not have a shearing strain. In other words, the element would not distort angularly, right? If you find this set of axes that is your principal set of axes. Okay, so what I'm showing on this diagram is sigma A, sigma B, and sigma C being my principal stresses, and epsilon A, epsilon B, and epsilon C being my principal strains. Right? Now, how much energy gets added on each face? Okay? Because what I did there, you might see that I had an equation earlier, I had a set of equations earlier to describe my strain relative to my stresses, and so I just applied that here, right? So I've got the strain in the kind of C direction here is equal to 1 over the elastic modulus times the stress in that C direction, but then subtracting off Poisson's ratio times the sum of the other two stress directions. So I just applied that here. My next question is, how do I know how much strain energy I have added into this system on each of my faces? Okay, and I'll give you a little hint. I just figured it out up here. And you don't have to do anything special, you just add them up. Okay, so each face where you're applying a stress, there's going to be a certain amount of energy that you impart to the element at each of those faces. And you just add that up. Your strain energy density is equal to 1/2 sigma A times epsilon A plus 1/2 sigma B times epsilon B plus 1/2 sigma C times epsilon C. Okay? Is that a question?
Yeah, so that those stresses are acting equal and opposite on other faces as well. When we're summing that energy, why do we not double it?
The reason why is that on each face, we are handling how much it has stressed and how much it has strained. Right, and so stress times strain on that face is going to give you that energy that's imparted at that face, right? We've already, I think the effect you might be trying to account for there, we are accounting for that by saying that we do have these strains that are functions of the other stresses, right? But yeah, we do get them accounted for, so that once we've got them accounted for, we can just add up 1/2 of each of the products of stress and strain for each of the faces. Okay? I see where you were processing that. All right. So let's actually substitute in some things, right? I know for each of my strains, I can actually say what each of those strains are as a function of stresses. Would you agree with that? So I can replace each of the strains that I have in my sum of strain energy density with stress values. And it makes a big equation, okay? That equation can then be simplified down a little bit, and it ends up giving you this equation right here, okay? 1 over 2 times the elastic modulus times, and then inside the brackets there we have the sum of the squares of each of your principal stresses. So keep in mind, these are principal stresses. I'm going to actually write that here because it's really important. Whoop. I better spell it right, though. Okay. Don't forget that that's what you need in order to use this equation. You need your 3 principal stresses in order to be able to figure out your strain energy density using this formula. Okay? Good so far? Let's work an example. Okay? Here's the example. Let's say that you know that you have an element of material, an element of glass as the material. All right? And that glass is experiencing the following stress tensor. Okay? So it has normal stresses of 1 MPa, negative 5 MPa, negative 2 MPa, and then shearing stresses of 3, negative 4, and 2 MPa. Okay? And what we want to do is find our principal stresses and directions. We want to find our strain energy density, and then also find the amount of energy carried in a piece of glass that has dimensions of 1 inch by 2 inch by 3 inch. That's our task. Here's what I want to do today, because last time we met, we covered how to solve this cubic equation. You might remember some of these equations that I have written down below here. We figured out how to solve this cubic equation using your Casio calculator, right? And I had another little note last time we met about, if we have time, we'll try to find our directions, our principal directions, right? In other words, find our direction cosines so that we know the directions of each of our principal directions. Okay? I'm going to actually do that today. Okay? But what I want to do here is, instead of use the Casio, I'm going to use Mathcad and show you some nice functions that you can use in Mathcad to get this done. Okay? So we kind of recall all of these equations right here, and then I had one more down lower that you can't see yet, where, or I guess two more down lower. One was recall that in the middle of our discussion of how to find this cubic expression, we wound up with this system, this 3x3 system. Okay, and you can go back and look at our notes from last time if you want to remember where that came from. We're going to need to use it again now. And then another equation that we're going to need to use is recall that our direction cosines were not all three independent of one another. And so we can relate your direction cosines according to this. And that shouldn't be 0. What should that be? 1. I don't know how I managed to mess that one up, but that shouldn't be 0. That should be 1. Okay? All right, so let's get into Mathcad. All right. So I've gotten the sheet started with stuff that I don't think that most people are going to struggle with. Okay? So I went ahead and loaded in my values for normal stress in my 3 directions. Okay? I've also loaded in my values for shearing stress in my 3 directions. Okay? From there, I went ahead and assembled a stress tensor. So far, so good? You with me? All right, and then just to make sure that I got all those values in there correctly, I went ahead and had it report to me what's in that stress tensor. And so that's what it's got stored in the stress tensor. Does that look like what we had for our problem that we were trying to work? Okay. All right, so our first step, just like we looked at last time, we have to find our stress invariants, right? So one of those, the first stress invariant, is the sum of the normal stresses. And you see that turns out for this problem to be -6 megapascals. All right, nothing tricky here yet. The next one, this one is one of the harder ones to remember exactly what's in there, although it does have a beautiful symmetry about it that might help you remember it, right? You basically just have each pair of products of your normal stresses added together, and then you have the square of each of your shearing stresses subtracted. Okay? And that gives you your second stress invariant. Notice there, what kind of units come out of that? Megapascals squared. Okay? So don't let that kind of confuse you too much. All right. I went ahead and left this part out because I wanted to show you how to get this part done. Okay? For the third stress invariant, do you remember what we did to find the third stress invariant? A determinant, right? You took a determinant of the original stress tensor. Okay? Well, good news is Mathcad can do determinants. And you use the little absolute value vertical bar kind of things, and then you load a matrix into there, and it will evaluate a determinant. All right? The only tricky part about this, so we're going to take the determinant of that stress tensor that I just called sigma. The only tricky thing about this is it's not going to want to see units in that number. Mathcad doesn't like that, to have units when it tries to evaluate these determinants. So what should I do? Okay. So stress, this sigma, is going to be in MPa. To get rid of that, I can divide by MPa. Okay? Makes sense? If I want to keep my MPa, all I got to do is multiply again out here. Whoop. All right? So that's a workaround for, the fact that Mathcad doesn't like to do determinants on values that have units. Okay? And what should I have done out here instead of putting MPa? Okay? This should be MPa cubed. All right? Which makes sense if you look at this expression, right? All of the terms in my cubic equation that I want to solve, okay, the very first one out there has a principal stress to the third power. So I'd better have MPa cubed come out of each of the terms in this, or else I'm not going to be able to add them together, right? So for I3, it's all by itself over there, so it better be MPa cubed. I2 better be MPa squared, because then you're multiplying by stress, right? And so on and so forth. All right. So the next thing that's tricky about this is you need a way to find all three roots of this cubic equation in order to know what your principal stresses are. All right? And your solve block doesn't really work that way, right? What does a solve block do? That's probably the thing you normally use to solve equations in Mathcad, right? You typically use a solve block. Why is a solve block not really good for this? Okay, solve block, you always do what first? You'd make an initial guess, and then it runs a guess and check technique behind the scenes, and then it finds something that makes your equations work. Well, here's our problem. There should be three things that make our equation work. The solve block will find one of them, and which one it finds will be a function of what we pick as our initial guess. Right? So we don't really want it to be that way. I want to introduce you to a new formula here, or a new function that's built into Mathcad. It's called polyroots. Whoop. I don't want it capitalized. Okay. So polyroots is a function built into Mathcad that what it wants you to pass it are the coefficients of a polynomial expression, right, set equal to 0, right, which is good because that's what we have, right? We just need to pass it the coefficients of this polynomial expression. And what it's expecting us to do is to pass it that information as a matrix. Okay? And so what we want to do is insert a matrix that is 4 values long. Okay? And you can look this up in the help file if you want, but what it's expecting you to do is to pass it these values from the least significant to the most significant. Okay? Meaning it wants I3 first. Okay? And again, you'd have to look that up in the documentation of this function to know that. But that's what it's looking for. And so what should I plug in here? Okay? Minus I3, right? Now, do you have any guesses as to whether polyroots is going to like my units? Okay, it's not going to like my units. All right? So what should I do? Okay, divide this by what? MPa cubed. Okay. For my next entry, what should I put in there? I2. And then that should be divided by what? MPa squared. For the third entry in here, I should have negative I1. Okay, that should be divided by MPa. And then what for my last one, which has now gone off my screen? 1. Okay, so let's see what this thing gives us. Excellent. All right, it's given me 3 roots to this expression. Now here's the thing. this, this function, or, this matrix of values that has spit out to me is in a particular order. Do you think I like that order? Why do you think I might not like that order? Not that it doesn't matter in terms of the outcome, right? These are the principal stresses. But what do you think I might not like about this? I probably want the order reversed. Okay? Let me show you something you can do here. I'm going to get rid of this again. Oop. And I'm going to cut this. And let me show you another couple of functions that might be helpful. There's a function called reverse, right? It takes a matrix or a vector and it reverses all the elements. There's another function that's called sort. All right? Sort orders the elements from lowest to highest. Okay? So I'm basically, sort would order from lowest to highest. I'm doing a reverse of that. It's going to end up highest to lowest. Okay? Which is what I want. So now I can just paste in here what I had from my polyroots, right? And then I should probably do one other thing, right? What do you think else what I should do for this? Okay? I should put my units back, right? And then maybe one other thing as well. Why don't I store this into another variable? I'm going to store it into sigma p. Okay, we good so far? Questions? Yeah.
Why did you flip the signs in the polyroots?
The reason I flipped those signs, negative, positive, is that's what's in the cubic that I'm trying to solve. Okay, I guess let me bring this to the front if I can. Okay, remember that's the cubic I'm trying to solve. The first coefficient is positive, the second coefficient is negative, third one's positive, fourth one's negative. That just came out of our expression that we derived last time. So the invariance, basically the way I did it is that I didn't store the signs into the invariance. I defined the invariance how I have them defined, and then for the cubic expression I have them plus minus, plus minus. Okay, so because I'm going to need it here in just a second, I defined another variable right here that is a particular value of principal stress. Okay, and I can pick out which value I want just by indexing this array. Right, so if I pick the 0th entry, and that's something you can change, by the way. If I wanted this to look more like 1, 2, and 3, I could change it to where it all indexed off of 1 instead of 0, right? I didn't do that in this case, but 0 is my highest positive principal stress, right? If I want to look at my other ones, I can put in a 1 here. That'll give me my next term in that expression, or I can put in a 2, right? Let me leave 0 in there for right now, meaning the most positive principal stress. All right, what we need to get into now is how do you go about finding the directions of your principal stresses? Okay, and here's what's tricky. You need 3 direction cosines to be associated with each principal stress. Remember, that's how we define directions in 3D, is you can define the direction of a vector with 3 direction cosines, right? So each of these principal stresses that I just found are going to need to have 3 values. Those are the direction cosines. Those 3 values will define the direction that each of those principal stresses goes. Okay? Well, let me show you how that can actually be done. You might remember, I wrote it up here just a second ago, you might remember this matrix equation from our derivation that we did last time. Okay, I mentioned it a few minutes ago. That matrix equation literally is just a way of encoding a system of 3 equations. right? And there are three equations where the variables are lambda x, lambda y, and lambda z. Those are your direction cosines. Okay? So that was, something that I had there is, a principal stress value minus a normal stress in the x. Here you've got minus your shearing stress in the xy, minus shearing stress zx and yz, right? Those are all supposed to be minus, even though the picture didn't come through real clear right there. All right. So you might see there that I've got the first two entries, I've got them entered as equations right here. Okay? Where I'm picking out just this one value of my principal stress to plug in for sigma p. All right? Why do you think I didn't put all three of them here? Okay? The reason I didn't put all three of them there is these are actually not all three independent equations. Two of them are independent, but the third one will be a linear combination of the first two. So we can't put in the last one in here because it won't be able to solve. Okay? What do you think we have to do to actually be able to solve this system? Go back and remember, do we have any other relationships that relate lambda x, lambda y, and lambda z? Okay. Yes, we do. Lambda x squared plus lambda y squared plus lambda z squared, even though I had it wrong at first on my notes just a second ago. What should this be? 1. All right. And Mathcad will solve that, and it will give you lambda x, lambda y, and lambda z. These are your direction cosines for your most positive principal stress. Okay? What do you think I have to do to get maybe my middle principal stress? Okay? I just have to feed this a different particular value, right? If I put this in as a 1, then it will give me direction cosines for that principal direction. All right? What if I put in a 2 here? Okay? That's my most negative principal direction, and those are the direction cosines that define that direction. Okay? Got a hand?
What are your blue lambdas? Where do we get?
Yeah, so from nowhere, I mean, these are initial guesses because you need that for a solve block, right? So the question was, where did I get these initial values up here? Keep in mind here that what we're solving, this is actually not a linear system of equations anymore. Why is it no longer a linear system of equations? Yeah, this last equation messes that up. So anytime you have a nonlinear system of equations, your initial guesses matter, or it could matter. Okay? For that reason, I didn't want to choose 0, and I didn't want to choose anything more than 1, and I didn't want to choose them all to be the same. Because any one of those conditions, I could imagine in my head some reason why any one of those conditions could throw off the solver. So I chose values that were between 0 and 1, because that's what the values will end up being, because they're direction cosines, right? They'll be between 0 and 1. And I chose them all three different from each other. But you might notice here, I could change this value, and it will probably not change the outcome, right? Now, that's actually not always totally true. It actually could change the outcome. How might it change the outcome? Okay, we talked about this a little bit right toward the end last time. Your direction cosines can actually be positive or negative of each other, right? If I have positive 0.455, negative 0.724, and positive 0.518, if I negate each one of those, then that also describes a line that goes the same direction as if all of these are the signs that they are. Does that make sense? So whenever you find these direction cosines, there are always two solutions. And neither of them are wrong, but I had to do some things for some of your online homework that y'all are going to do. I had to do something to be able to get you to know which way to enter them. And so I went ahead and used, I can't even remember what standard, but I used some kind of a standard that says, I think I may have done something like your highest value, make it positive or something like that, and then report all the other ones according to that one. Okay? All right. Isn't that cool?
Would you just do arc cosine of lambda?
If you wanted to figure out the actual angles, then yes, you could take the inverse cosine of any one of these and you could figure out the actual angle from one of your original coordinates, x, y, or z, to the axis that you have now found for this principal direction. Okay? All right. Now I'm going to do something that might make you hate me a little bit. Okay? I've shown you all the long way of how to do all this stuff. Okay? Now I'm going to tell you what it is that we've been doing. This is a classic eigenvalue, eigenvector problem. All right? And you might remember that from, it may have been in your differential equations class or something like that. But this is a classic eigenvalue and eigenvector problem. What do you think the eigenvalues are? Okay? For your original matrix, the eigenvalues of that matrix are your principal stresses. Your eigenvectors are the directions of each of your principal stresses. Okay? Well, Mathcad also has eigenvalue stuff that it can do. Okay? But I didn't want to start there because I wanted you to appreciate, how you get there, right? All the stuff that's going on back there that's making this happen. And there's a really fast way for you to get eigenvalues and eigenvectors, and that gives you principal stresses and principal directions. All right? For this, if I wanted to get an eigenvector in a different direction, what do you think I would do? Right? So, I figured I'd show you that so that you weren't in the dark about the fact that you can do eigenvalue problems directly in Mathcad. Again, be mindful that it doesn't like units in that particular numerical technique that it's using there, so strip the units and then you can put them back later. All right, but this wasn't our entire problem, was it?
No, we need the energy carry.
Okay, we need our strain energy density, and then also the total amount of energy density. So we'll get back to that. While I'm trying to get back to that, let me also actually make the comment that I have another video that is posted that shows you how you can get these principal directions if all you've got is a Casio FX115 ES Plus. All right, there's another technique that you can use to do that. It can't do this exact technique. Why not? Yeah, once you go to this nonlinear equation for that third equation right there, your Casio can't do a system that has a nonlinear expression in it. Right? So that messes it up. The solve block is fine with it, but your Casio's not. So there's a whole other technique that I show in a video that's posted, and so you might want to check that out if you want to learn how to do it with just a Casio. All right, so back to our original problem. We now have our three principal stresses, and what we're supposed to find is a strain energy density. Okay, let me actually go up here and grab the strain energy density equation. Bring it down here. Okay, and write down what my three principal stresses were. What was my first one? 4 MPa. What was my second one? Okay, 1.6. I'll go ahead and look over here. 1.683. You were exactly right. And then my last one was negative 8.317. Okay, so now let's find our strain energy density. All it is just plug and chug at this point. Okay, so strain, I don't have a good letter for strain energy density, so I'm just going to abbreviate it SED. Okay, strain energy density is going to be equal to 1 over 2 times. Where do I get my elastic modulus for glass? Okay. We go back again to table A5. Table A5 has an elastic modulus listed for glass. It says that it is going to be 46.2 GPa. Okay, I'm going to write this as 46.2 times 10 to the 9th pascals. Okay, and then in here I'm going to put the square of my first principal stress, right, 4 MPa. Okay, I'll take that and square it. Next one's going to be negative 1.683 MPa. That one squared. The next one's going to be negative 8.317 MPa, and that one will be squared. Then what? Minus, okay, minus 2 times nu. What's nu? I don't know. What's new with you? Okay, it is your Poisson's ratio. Okay. So Poisson's ratio is 0.245 for glass, according to table A5. Okay? And that's unitless. Okay? So let me just go ahead and say here, table A5 is where I got that elastic modulus and this Poisson's ratio. All right, now need to multiply this now by what? The product, the pairs of products, right, of each pair of my normal or my principal stresses. Okay, so 4 MPa times negative 1.683 MPa plus 4 MPa times negative 8.317 MPa. Okay, and then lastly plus negative 1.683 MPa times negative 8.317 MPa. Okay? And so my strain energy density can be calculated like this. Okay? Let me do it this way. Let me actually load each of my principal stresses into variables in my calculator. And I'm going to do this in base units. Okay? So my first principal stress was 4 times 10 to the what? 6th. Okay? And I'm going to store that into A. Okay? What about my next one? Negative 1.683 times 10 to the 6th. I'm going to store that into B. Okay, and then the next one was negative 8.317. All right, times 10 to the 6th. I'm going to store that into C. Okay, while I'm here, let me also store my elastic modulus. I'll store it into E. Okay, 46.2 times 10 to the 9th. All right, so now when I enter this in my calculator, it should be relatively easy. 1 over 2 times E times, okay, here I have A squared plus B squared, oops, plus C squared, okay, minus 2 times, okay, my value for Poisson's ratio is 0.245. Okay, times, here I've got A times B, plus A times C, plus B times C. Okay, and I hit enter. So what I did there, just to kind of be clear, I actually had Pascals for all my units because I put in my values with the multipliers of like 10 to the 6th or 10 to the 9th, right? So since I put them in that way, all of my units here are in Pascals. So how do I interpret my answer here? Okay, if you look at this, we have basically what we're going to have is Pascal squared in the numerator, because that's all the terms in the brackets in here are they're going to be in Pascals squared, and then that's going to be divided by what? Pascals. So it ends up being Pascals. So when I look at this value that I just got out of my calculator, 1090.3, we'll just say, that's in Pascals. Well, is that right? I mean, do you measure strain energy density in Pascals? Okay, let's see if we measure strain energy density in Pascals. Okay, so a Pascal is what? It's a Newton per square meter. Okay. Well, that gets rid of my Pascals. What if I now multiply this by a meter per meter? What does that do for me? Okay. What I've now converted this to is, okay, I have a Newton meter per meter cubed. A Newton meter is what? A joule, okay? Newton meter is a joule, okay? And so this ends up being joules per cubic meter. All right? So far, so good there. That is my strain energy density. But then what? What else were we supposed to find up here? Okay, we've got some dimensions of a piece of material that supposedly is carrying this type of stress, this stress tensor. All right? Well, what do I do to figure out the amount of total energy carried in that block? Take your strain energy density and multiply by volume. All right? So that energy okay, I'll call it strain energy maybe, is just going to be equal to 1090.3 joules per cubic meter times 1 inch times 2 inches times 3 inches, because we said it was a 1 inch by 2 inch by 3 inch block of material. So now what do I need to do? Got to convert, right? So what's my conversion from inches to meters? Okay, well it's 2.54 centimeters per inch, right? Okay, and so you would cube that, but 2.54 centimeters is 0.0254 meters. Okay. And we cube that. All right. And I think I have that written down somewhere. I don't know. I'll go ahead and plug it in. So let's see. We have this value times 1 times 2 times 3 times 0.0254 raised to the third power. Okay? So that means our little block of material that has this stress tensor on it is carrying 0.1072 units, joules. All right, fair enough. Let me ask you a quick question. If you wanted to figure out how much this little element changed in volume, you might look at me and go, what? Change in volume? Oh yes, change in volume. Okay, how do you figure that out? Let me ask you this. Do you know the strain in each direction? Okay. So if you know the strain in each direction, all right, then you should be able to figure out the amount of change in length in each direction. And so you should be able to figure out an original volume just with your dimensions, and then figure out a change in length in each direction. Right? That gives you a new length in each direction. And then what do you do with that? All right? Multiply all three of those together. Now you have the volume that your element has become. So that's how you could deal with that. I half wanted to kind of explain what you would do with that, and I half wanted to just even introduce the idea that stress and strain can change the volume of material, because that's not something that would necessarily be obvious. It will change the density as well, because mass will remain fixed, right? We're not creating or destroying mass in that process, but changing the volume. All right, any questions?
For the strain energy density, is that something that's like tabulated to figure out how much material can hold?
So the question was, for strain energy density, is that something that's tabulated to know how much of that something can hold? The answer to that is no, not really. What it is it's actually going to be a stepping stone to understanding. Okay, so I want you to kind of understand that these materials carry strain energy as a result of them carrying stresses. As a preview of what we are eventually going to do, I would say our best failure criteria, static failure criteria, the best static failure theory that we use is called the distortion energy criteria. Okay, so that's where we're going with it, but it's not quite as simple as just saying, well, you have a certain amount of energy, so it's going to fail. It's going to be a little trickier than that. All right. But that video is already out there if you want to watch it. So I will see you guys next week.